everybody, and welcome back for Unit 5, Lesson 8. The topic of this lesson is going to be analyzing f of x, so the original function, using the graph of f prime, the graph of the derivative. We have one learning target for today, and that learning target is going to be I can use key features of the graphs of f prime, and f double prime to determine how graphs are related to one another. So, one of the big connections that we've been making throughout this unit is the connection between the original function and the graph of f prime. What I'd like to do now is just review those connections. I'm going to go through this pretty quickly because it is a review of something we've already talked about. And then we're going to look at some example problems of what you might see on like an assessment like the AP test or an assessment like what we're going to give you in class, where we're going to ask you to make some of these connections. And we're going to practice making those connections and justifying our reasoning. So just as a review, if we're talking about a graph and I say, where are the critical points? The critical points are going to be the places where the derivative is equal to 0 or does not exist. So you're going to be looking for either maximums or minimums. Those would be places where the derivative is equal to 0. And you're going to be looking for where the derivative does not exist, which means corner, cusp, vertical tangent, or discontinuity. On this picture, the critical points would be here and here. If I ask you, where is this graph increasing? Increasing is going to be the parts of the graph that are going uphill. So increasing is going to be where we see a positive slope, which is right here and right here. I should highlight all of these. And if I ask you, where is this graph decreasing? Decreasing is going to be the parts of the graph that are going downhill because the slope is negative, which in this case would be this middle part of the graph right here. Now, what I'd like to do is compare that to what we look for on the graph of the derivative. So if you don't have this graph, and you just have the graph of f prime, how could you still find the critical points of the original and whether the original is increasing or decreasing? Well, when we're looking at the derivative, the critical points are now going to be the x-intercepts of the graph. So in this case, that would be at pi over 2 and 3 pi over 2, which you'll notice are the same x values that we had before, only they have become the x-intercepts of this graph. So that would be at x equals pi over 2 and 3 pi over 2. Now, if we're looking at the graph of the derivative, we're going to know that the original graph was increasing when this graph is above the x-axis. So in other words, the derivative is positive, which would be right here and right here. So those intervals, and we do always use closed intervals here with very few exceptions, we would have 0 to pi over 2 as well as 3 pi over 2 to 2 pi. And last but not least, decreasing is going to be the places where this graph is below the x-axis, which would be right here in between, which would be from pi over 2 to 3 pi over 2. So again, we're figuring out where the original is increasing, the original is decreasing, the original is critical points by looking at these features on the graph of the derivative. Next, let's talk about kind of second derivative information. So if we're looking at a function and I say, where are the points of inflection? That's going to be the places on the function where the concavity changes. So it's really important to realize that this is where the concavity actually changes from concave up, looking like a cup, to concave down, or looking like a frown. In this case, that would be when x is worth pi. We are going to be concave up when the graph is shaped like a cup. So over the interval where the graph is shaped like a cup, which in this case would be this interval here. And we're going to be concave down when the graph is shaped like a frown, which in this case would be this interval right here. Now, how does that compare to what you would look for if instead of having the graph of the original, you had the graph of the derivative? Oops, I'm so sorry, this is a typo. This should say points of inflection. it should say, and then concave up and concave down was fine. JK, that was fine. So for points of inflection, if we're looking for points of inflection on the graph of the derivative, this is going to be the place where the slope of f prime changes signs. So that in this case would be right here. Now you'll notice it's the same x value, which is pi, that we identified here. It's just we're looking for something different because it's the derivative graph instead of the original. This graph is the original is going to be concave up when the slope of f prime is positive. So we're looking for where this graph is going uphill, which is right here, this section of the graph. And we always use open parentheses when we're naming these. So we would say from pi to 2 pi with open parentheses. And we would know that the original graph is concave down when the slope of f prime is negative. And so that would be this first section of the graph right here, which again, we use open parentheses, so 0, comma, pi. Now, if you look at the intervals, it's the same intervals between 0 and pi, this graph was concave down. Between 0 and pi, this graph was going downhill. It's just we're looking for different things because we're going to have the graph of the derivative instead of the graph of the original. You should also notice that in every single one of these, we're talking about the slope of f prime. For points of inflection, it's when it changes signs. For concave up, it's when the slope of f prime is positive. And for concave down, it's when the slope of f prime is negative. So we're always looking at the slope of f prime, which makes sense because the second derivative would be the slope of the first derivative. So what does this look like? How would we do a problem using all of these connections that we've been talking about? Well, I'm going to tell you on an assessment like the AP test, 99 times out of 100, you're going to be given the graph of f prime. So it's really important to realize that you are almost always going to be looking at the graph of f prime, not the graph of the original function. We are told here in the directions that the figure below shows the graph of f prime, which is the derivative of f, on the closed interval between -1 and 5. Now that just means that the graph actually stops here at the endpoints. We're not assuming that it stops. We're telling you in the instructions. It stops at -1 and it stops at 5. Find the information using the graph, justify all of your answers. One of the big keys here is that we are going to be asked to justify when we find these features, so we need to practice doing that using the right symbols and vocabulary. Let's start with critical points. So critical points, if we're looking at the graph of f prime, are going to be the x-intercepts, the places where the derivative is equal to 0. So I would say that f of x, the original, has critical points at x equals 1 and x equals 4 because the derivative f prime of x, which is what we're looking at here, is equal to 0. And that's what makes it a critical point. Now let's do increasing. So we'll kind of start with all like the first derivative stuff, basically. Let's do increasing. So this function's going to, or the original function's going to be increasing on the sections of the graph where the first derivative is positive. So the original function's going to be increasing right here because that's where this graph is positive. It's above the x-axis. So we would say f of x is increasing on the interval from 4 to 5 because the first derivative, which is what we're looking at here, is greater than or equal to 0. It's above the x-axis. Now let's talk about decreasing. So decreasing is going to be where is the first derivative negative. So that's going to be this entire part of the graph. It's always below the x-axis this whole time. So we would say that f of x, the original, is decreasing on the interval from -1 to 4 because the first derivative, which is what we're looking at here, is less than or equal to 0. Now let's jump over and talk about points of inflection. So points of inflection are going to be places where the slope of f prime changes signs. So that's going to happen at this point right here, where the slope changes from going uphill to downhill, and this point right here, where the slope changes from downhill to uphill. So points of inflection, we're going to say f of x has points of inflection at x equals 1 and 3 because the slope, so we're talking about the slope of f prime of x, which is what we have here, changes signs. Now, for concave up, we're going to be looking for where this graph is increasing, so it has a positive slope. So concave up is going to be asking, where is this graph going uphill? That's going to be this section of the graph right here. So the original function is going to be concave up, so f of x is concave up. On the interval from 3 to 5 because the slope of f prime of x is positive. Last but not least, where would the original graph have been concave down? Oh, I'm sorry, there's another interval here where it's concave up. I almost missed it, which is right here. We have a positive slope here, and we have a positive slope here. So I should add that interval from -1 to 1. Now the last question here is going to be, where is the original graph concave down? So the original graph is going to be concave down when the slope of this graph is negative. So we're going to be looking at this middle section of the graph right here. Now I'm not going to write this answer in yellow because I think it's kind of hard to see. I'll just go ahead and write that in black. So we would say that f of x is concave down on the interval from 1 to 3 because the slope of f prime of x is negative. Now, one of the things that we have learned earlier in this unit, but that we haven't talked about yet today, is the idea of having a relative max or a relative min. So what I'd like to do is kind of review those ideas with you, and then we will write down where the relative maximums and the relative minimums would be. So a relative maximum is going to be a place where the original function changes from going uphill to downhill, or in other words, on this graph, we're going to be looking for where it changes from above to below the x-axis. If we look at this graph, that's going to happen right here when x is 4. So we've got a function that's above to below doesn't happen at all on this graph. So there's going to be none. There's going to be none for our relative maximums. But the relative minimum, where we change from below, there we go, I can do it, to above, is going to happen when x equals 4. And we would say because f prime of x changes from negative to positive, which is, in other words, below to above. So you can see we're below, which means we have a negative slope, changing to above, which means when the original has a positive slope. Okay, let's do one more. This is a very typical AP test question. It says the figure below shows the graph of f prime on the closed interval from -5 to 5. So again, we have the graph of the derivative, and again, it's telling us in the directions it stops at the edges. Find the x-coordinates of each point at which f of x has a horizontal tangent line, and then for each of these points, determine whether f has a relative min, max, or neither a max or a min at that point. Justify your answers. So this first question actually has multiple parts. First, we need to find the x-coordinate of each point at which f of x has a horizontal tangent line. So a horizontal tangent line is a place where the slope is 0. In other words, we're looking for where f prime of x is equal to 0, which is going to be here, 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 and here. So we would say f of x has horizontal tangent lines at x equals -5, -3, 1, and 4, because those are the places where the derivative is equal to 0. And again, we're going to have a horizontal tangent line, which means the line is horizontal when the slope is 0. Now, for each of those points, we need to know whether we have a relative minimum, maximum, or neither. For the point at -5, since that's an endpoint, we're going to have neither a relative min or a relative max, because relative maxes and mins cannot occur at endpoints. So I would say at x equals -5, we have neither a max or a min, because that is an endpoint. And you can only have relative maximums and mins at points that are not endpoints. Next, let's look at -3. So at -3, this graph changes from above to below. That means the original graph is changing from a positive slope to a negative slope. So what that means is that at x equals -3, the original graph would have had a maximum because we're changing from a positive slope to a negative slope. So we would say at x equals 3, f of x has a relative max because f prime of x changes from positive to negative. Now let's look at what's happening at 1. So at 1, we're changing from below to above, which means a negative slope to a positive slope. So that's going to be a min. So we would say at x equals 1, f of x has a relative minimum because f prime of x changes from negative to positive. And last but not least, we would look at the x equal 4. We're changing from above to below, which is a positive to a negative slope on the original. So that would again be a max. So we would say at x equals 4, the original graph f of x has a relative max because f prime of x, the derivative, changes from positive to negative. Okay. Next, it says find the open intervals over which the function is both increasing and concave down. Justify your answer. Now, the first thing is it says open intervals. So it's basically just reminding you to use parentheses when you write your answers. So it's giving you a hint over which the function is both increasing. So increasing means that f prime of x is greater than or equal to 0, which means, in other words, we're going to look for where this graph is above the x-axis. And concave down, which is going to be where the slope of f prime of x is negative. So we're going to be looking for where this graph is both at the same time above the x-axis and also has a negative slope. Now that's going to happen 2 times. It's going to happen right here, where you're above the x-axis but you have a negative slope, as well as here, where you're above the x-axis but you have a negative slope. So we would list the intervals -4, -3, and also 2, 4, and then we need to justify our answer. So we would have to justify both why we know that our function was increasing and why we know that our function was concave down. So we would say because f prime of x is greater than or equal to 0, that is the reason that we know that the function was increasing, and the slope of f prime of x is negative. That is the reason that we know that the original function was concave down. So you're basically combining these 2 reasons. The things that you looked for are the justification for what you found. Finally, last but not least, it says find all of the x values on this interval at which f has a point of inflection. Now, a point of inflection is going to occur at a place where the slope of f prime of x changes signs. So I'm going to go back to this graph and I'm going to look for the slope changes from positive to negative or negative to positive. That's going to happen once right here at -4, again right here at -1, and again right here at +2. So I'm going to go ahead and write those values down. So I'm going to say x equals -4, -1, and +2. And then I would say because the slope of f prime of x changes signs. All right, thank you guys so much for watching, and we will see you soon for some practice.